The Earth is a sphere spanning 360 degrees of rotation. To complete one full turn on its axis, the planet takes 24 hours. Dividing those 360 degrees by the 24 hours in a day reveals a constant physical relationship. The Earth rotates exactly 15 degrees every hour. These 15-degree increments create a geometric grid across the Earth's surface. This grid ensures that time zones remain tied to the planet's physical rotation rather than arbitrary boundaries. We can use this relationship to find the exact time at 90 degrees east when it is currently 2 p.m. at 30 degrees east. Step 1 is to find the gap. We subtract 30 from 90 to identify a 60-degree longitudinal difference. Step 2 is to divide by 15. Dividing that 60-degree gap by 15 converts the geographic distance into a time difference of exactly 4 hours. Step 3 applies the directional rule, east increase. Adding 4 hours to 2 p.m. results in 6 p.m. Following these 3 steps, finding the gap, dividing, and applying direction, provides a reliable procedure for any time zone calculation. At the Prime Meridian, coordinates switch from west to east. Simple subtraction fails to find the true gap when comparing locations across this 0-degree line. Consider the distance between 30 degrees west and 30 degrees east. On a linear scale, these points are not at the same location, yet subtracting 30 from 30 would suggest there is no gap at all. To find the true gap when crossing 0 degrees, you must add the absolute values of the two coordinates. Adding 30 and 30 reveals the actual 60-degree difference. The rule remains consistent. Subtract if the locations are in the same hemisphere, but add them together whenever they bridge the prime meridian. Complex calculations often involve shifting days. If it is 4 p.m. at 120 degrees west, we can determine the time at 90 degrees east by tracking both the hour and the date. First, we find the gap. Since we are crossing 0, we add 120 and 90 to get 210 degrees. Dividing that by 15 results in a 14-hour time difference. Now apply the eastward increase. Adding 14 hours to 4 p.m. requires careful counting. Moving forward 8 hours brings the clock face to 12. Reaching 12 signifies midnight. This rollover automatically advances the calendar to the next day. We then add the remaining 6 hours of our difference to midnight. The final result is 6 a.m. on the following day, illustrating how large longitudinal gaps frequently cross calendar boundaries. Pause here to test the process. If it is 10 a.m. at 75 degrees west, what is the time at 60 degrees east? The gap is 135 degrees, creating a 9-hour difference. The answer is 7 p.m. the same day. Physical travel introduces a final variable. Departing 120 degrees west at 4 p.m. on a 6-hour flight to London requires determining your exact landing time. To solve this, use the portal method. Convert your departure time to the destination's time zone before accounting for the flight. London is 8 hours east of 120 degrees west. This means at takeoff at 4 p.m., it is already midnight in London. Now add the 6-hour flight duration to London's time. You will touch down at 6 a.m. local time. Always establish the destination time zone first, then add the physical duration of the travel. At 180 degrees longitude, we reach a mathematical collision. This is the point where the hours added by moving east meet the hours subtracted by moving west. This collision is resolved by the international dateline. Crossing this boundary while moving west advances you by 1 day, while crossing it moving east returns you to the previous day. This line functions as a necessary reset point, allowing a rotating sphere to maintain a consistent linear calendar. Global time logic relies on 4 consistent operations. Find the gap, divide by 15. Apply the east-west direction, and for travel, always convert the destination time first. Executing these steps in sequence removes the confusion of shifting hemispheres and ensures accuracy across any distance on the globe.